very sorry. I don't speak very good Chinese or at all. But I'll try to be at least reasonably understandable in English, and hopefully there's a lot of people here who can help facilitate questions. And in any case, if you have questions during my talk, please feel free to interrupt me. If you want. So I'm going to talk a little bit more about the Event Horizon Telescope observations that we took, that we keep taking every year, cross our fingers hopefully, and specifically about the first results that we published, both on M87, which is the first black hole image, and the Sagittarius star, the black hole at the center of our own Milky Way. So just a little bit of review. I think I couldn't really understand a lot of what he was talking about, but from the pictures he showed, I think he talked about this a lot. What are black holes? Black holes are there's two definitions depending on what gravity theory you want to talk about. So black holes exist in Isaac Newton's theory of gravity, where gravity is a force that pulls on objects. And there, a black hole is just an object whose gravity is strong enough that the escape velocity is equal to or greater than the speed of light. And so this is, this is where black holes were first sort of imagined. There were ancient writers back in the 17th century who talked about what if you had a star that was big enough that its light that it emitted couldn't even escape. But then, of course, as time went on, our theory of how gravity worked evolved, and Einstein proposed probably the most successful theory yet, which is the theory of general relativity. And his argument is gravity isn't a force, it is actually just the curvature of space-time. And so a black hole instead there will be an infinite curvature of space-time. And in this case, there's a couple of quantities you might think about. There's, of course, the event horizon, which is described by the Schwarzschild radius. And this is the region where the curvature of space-time can only allow for orbits and motions of particles that are at the speed of light. And of course, space-time itself, you can imagine it is at every point around you as a ruler and a clock. And so as curvature changes, the length of the ruler will change, and the ticking of the clock will change. But of course, this is only for external observers. If you have a ruler and a clock, no matter where you are, your ruler will always be 1 meter long, and your clock will always tick at 1 second. This is a very subtle thing about general relativity, but there's a rule that you can always transform your own position in rulers into a locally flat spacetime. But of course, if you look at someone else who's further away from you, and they're closer to, say, a black hole, their ruler will be a different length, and their clock will tick at a different time. And so if we get into black holes, there's really two types of black holes. There are what we call stellar mass black holes, or black holes that are sort of the size of stars. And these are the remains of the largest stars in the universe. So if a star is born of 100 or even a couple of hundred solar masses, eventually its life cycle will lead it to die a very violent death and leave behind a core that is 3 or 4 times the mass of the sun, and that object will be a black hole because it's so massive and dense that it will trap all light that escapes from it. There's another method of creating black holes that we think exists, but we're not really sure yet, and that is generating supermassive black holes. And we think that at the Big Bang, there were lots of little nuggets of matter that collected together and formed giant seeds of mass all at once. So instead of forming a star first or a galaxy, it just all collapsed together and immediately formed a black hole that is 100,000 to 10 billion times the mass of the sun. And we think that these things occurred very early in the age of the universe. Maybe some of them even started at the start of the Big Bang. And of course, remember, one solar mass, or the mass of the sun, is equal to 2 times 10 to the 30 kilograms, or 300,000 Earth masses. So of course, when we talk about 10 billion solar masses, that is another 9 factors of 10 on top of the mass of the sun. So Heng-Yi, of course, talked about the event horizon and the Schwarzschild radius, but this is maybe another example to give you an idea of what the size of an event horizon means. So I think Heng-Yi, I couldn't really understand, but I noticed some text in a slide that said 3 kilometers, right? And so the Schwarzschild radius has an easy conversion, very easy for us. Every solar mass gives you 3 kilometers of Schwarzschild radius. And so that means the event horizon for a solar mass black hole is going to have a diameter of 6 kilometers. And if you place that over, where we live, this is the size of that object. And so you can think about, if the sun were replaced by a black hole, that black hole's event horizon would only be this big. And of course the sun is huge. Right? And of course much smaller than the size of a planet. Now, of course, the important thing about black holes is that they don't, we don't actually see the event horizon, but instead we see the shadow of the event horizon. This is sort of a movie that shows this. You can see a grid of space-time. The curvature will shrink the rulers. And you can see light rays traveling around the black hole that are bent by the curvature of the black hole. And because they're bent, they will sort of deflect around. And not all of the rays of light will come back to the observer because they'll get captured by the black hole. And so this causes a shadow of all the light around the black hole. If there's a disk around the black hole, you can't see all the light coming from that disk. This is what we mean by shadows. And of course, the center of that shadow is hopefully very dark. And so this is what the shadow of a one solar mass black hole would look like. I think Heng-Yi put a conversion on there maybe, where if you take the event horizon, the shadow is about 10 times larger than the event horizon. And so you go from, or 2 times larger. So you go from 6 kilometers to about 14 kilometers. But of course, we're not really, it's very hard to look at a shadow of a black hole that's 14 kilometers in diameter. If you had a stellar mass black hole, even if it was just at the center of our solar system, you would need a much bigger telescope than the Event Horizon Telescope to look at it. And so we decided to look at much larger black holes, the supermassive black holes. And of course, there are trillions of galaxies in the universe, almost uncountably many, and our galaxy is just one. At the center of every one of these galaxies is a supermassive black hole, and they're like I said, they're extremely common, and so this is a great place to look for them if you want to find them. And of course, our galaxy has its own black hole. The sun, of course, is located sort of relatively far out in the disk of the Milky Way, about 27,000 light years, or 8 kiloparsecs, where a parsec is about 3 light years. And we've been studying the galactic center for a very long time at almost all frequencies. And in fact, a lot of people here in Taiwan have been studying the galactic center black hole for a long time, especially in radio wavelengths. The other object that we care about is M87, which is 51 million light years away from us, or 17 megaparsecs. It is, in fact, the largest galaxy in what we call our local group. So we have a group of galaxies all around us, and M87 is the biggest one of them. It is sort of the center of our neighborhood, or downtown, so to speak. And of course, because it's the largest galaxy, it also has the largest black hole inside of it. And in fact, it's almost one of the largest black holes in the whole universe. It's sort of a special coincidence, or maybe we just got lucky, that right in our own neighborhood is one of the largest black holes ever measured. And of course, one of the other interesting things about M87 is that there's a very prominent jet of material that comes out of the center at a lot of different wavelengths. And so to look at this object, we're going to use radio telescopes. And of course, Asia A has been a pioneer in developing radio telescopes for, the better part of 50 years now. And of course, we manage and develop instruments for these telescopes in Hawaii at the JCMT and the SMA. We spend a lot of time in development supporting the ALMA telescope project in Chile. And of course, we now have a telescope in Greenland that we share with the Smithsonian Institute in the US. And I think I'm actually going to Greenland at the end of March to help with observations for this year. So it's going to be very exciting. And so what we do is we connect all these telescopes together into the Event Horizon Telescope, a global millimeter, very long baseline interferometer. And so the idea here is when you have multiple telescopes all looking at the same object, you can correlate the signals from those telescopes, match up the signals, and then you can get increased resolution and sensitivity. And so, there's the Asia A contributes to approximately half of the telescopes that are used in the current EHT array. And you can see here Kevin Koei and Satoki Matsushita, who are here from Asia A at one of the nights in Hawaii for the first set of observations. And so in basics, the idea behind interferometry, like I said, is you get a signal from a very distant source, and those light rays will come towards the Earth that are essentially in parallel lines. And so if you have a telescope in Mexico, in this case, well, it's not quite to scale, a telescope in Mexico and one in the South Pole, then they will see this light from the same source. And if you know the exact positions of the telescopes and the exact time you got the signal using GPS clocks, you can synchronize that signal. And actually, what's kind of interesting is at these telescopes, the signal they measure is just a voltage over a receiver. And they only measure the voltage at 4 positions, which is, you think that's not enough detail to be able to describe all of this thing, but the trick is they measure this 4-position voltage 1 billion times a second. And so they get very rapid information. And so you take this data, and because you record it so fast, you collect a lot of data. So any given night of observation will generate a petabyte of data, which is tremendous. It's way too much to send over the internet, and so we take big towers of hard drives and stick them on a plane and fly them to the data processing center, either in Boston, Massachusetts, or in Bonn, Germany, and then they plug their hard drives into their supercomputers and take the signals that are frozen in the hard drives from one telescope and another telescope and try to match up the voltages to get a signal from the source. And so once you do that, it goes through a bunch of other data reduction pipelines, and you get the actual interferometric data that we use for imaging and model comparison. So this is sort of the movie I think that Honeywell showed about this process of assembling all the telescopes together. And so as the Earth rotates, it fills in more of this UV plane, this Fourier domain plane, and gives us better coverage of the source itself. This actually is the coverage for Sagittarius star, the black hole at the center of our own galaxy. And so why do we want to look at 2 objects? Well, the 2 objects are actually very different, even if they might be explained by the same theory. So again, I think Heidi mentioned this. M87 is much further away, but it's much larger. Sagittarius star is smaller but much closer, and so on the sky they appear approximately the same size. 40 microarcseconds compared to 50 microarcseconds. And the other interesting thing is that because M87 is so big, you think about a large object, it's much harder for it to rotate very fast, right? And so it's actually much slower in the sky. It'll complete a full rotation in a week or so. Whereas Sagittarius star, it's much smaller, and so it'll complete a full rotation in a minute. So the speeds of these objects are very different. This is another sort of analogy. You can think of M87 as your big family dog who's old and lazy. It lays down a lot, it's not very active, and so it's very easy to take a picture of it. Compared to Sagittarius star, which is a new young puppy, very small, active, chasing its tail all the time. And so whenever you take a picture, it's very blurry. The other issue, of course, is that there's this other complication for Sagittarius star. Because we live in the same galaxy as Sagittarius star, we have to look through our own galaxy and our own dust and our own debris. And so that causes sort of a screen effect and blurs our image as well. So it's not only just taking a picture of a fast dog, where your shutter speed isn't fast enough to capture the motion, but you also have to look through it through a foggy piece of glass. Whereas M87, it's far away, we're seeing through less material, and so it's a little bit clearer. So getting back to M87, so this is the first object we looked at, and here you can see all the other observations that happened at the same time as the EHT. So we observed it in X-rays with the Chandra Telescope and NuSTAR, as well as a couple of very high energy gamma ray telescopes. And here in the X-rays, you can see that there's this very long jet that comes out of the center of the black hole. This is material that's being ejected at essentially light speeds. We're very close to light speed away from the black hole. And here you can also see it in infrared at the top, all the way down to optical light, in this case blue light by Hubble. And again, you can see this very long jet extending out of the center. And then in radio, you have the ALMA observatory at 1 millimeter, and then you have 13 millimeters, 7 millimeters, and 3 millimeter observations at a bunch of different other telescopes. And in fact, many of the telescopes used at these other frequencies are the same ones that we use for the EHT. You just, again, you can think of frequency as color, right? So at optical wavelengths, red light has a longer wavelength than blue light. And so even though blue light has a higher frequency, it's got a shorter wavelength and a different color. So the same thing here for radio telescopes. At 1.3 millimeters, or 230 gigahertz, which is the frequency, is a different color than 7 millimeters, which is a different frequency of radio. And so you can think of this, even though it's all displayed in orange, these are all many different colors, technically shown in the radio. And so this is the first picture of a black hole. This is M87 star, taken from data collected in April 2017. And because it was our first attempt, it took us a very long time to analyze the data, and we published this in 2019. And so we used a variety of different methods, at least 5 different imaging methods, to make sure that we were all agreeing with each other. And we found that the black hole size was about 40 microarcseconds. And we also compared it to a bunch of different state-of-the-art fluid simulations to check to see if those simulations had any reasonable agreement with what we actually saw. And it turns out they were pretty good. Perhaps one of the most important parts of this observation was that we were able to settle a long-standing issue in terms of M87 science. There had previously been 2 estimates for how massive the black hole was. One using the orbit of gas around the central object, and one using the orbit of stars. And they disagreed. One said that the black hole was 3.5 billion solar masses, and one said it was 6 billion solar masses. And so the EHT came by, and because we were able to take a picture of the black hole, measure the diameter, and using the size of the shadow and the relation with the Schwarzschild radius, relate that exactly to a mass. And we were able to break the degeneracy here, and we said that the mass should be 6 billion solar masses. And so we solved a long-standing problem in astronomy related to M87. Now getting on to Sagittarius Star, we took this data at essentially the same time as M87, but we published it only last year. Because again, it's a much more challenging problem because Sagittarius Star spins so much faster and is so much more variable. Again, with M87, we could average all of our data into one single snapshot, whereas with Sagittarius Star, as we try to, the Earth rotates and fill in our space, Sagittarius Star is changing and looks different before we can take a whole picture. So we had to really change a lot of our instruments to be able to account for that variability and do a clever type of averaging of our data to make sure that we weren't sort of smearing out too many important details. And so of course here is our final picture. It's a little bit different than M87. You can see that it's not very, it's much more symmetrical than M87. M87 was dim at the top and bright on the bottom. This is more sort of even. But the other important thing is that we can't really settle on where the brightest points live. So here is one example of a good image, but here are also other examples of good images. And so you can see these bar charts at the bottom represent the fraction of images that represent this type of structure. So you can see most of the images look like either this guy or this guy, but these are both equally good fits to the data. And so the bright spot could either be down in this corner or in this corner. But there's also this mode where the bright spot is this corner. And all of these are equally fine fits. And so it's not really clear to us exactly where the brightness should live in the azimuth, in the angular profile of the black hole. Mainly because a lot of our different methods do different ways of averaging the data. And so one method may be biasing some of the data, another method may be biasing other components, but at the end of the day, they all get equally good fits. And again, we can compare them to a bunch of different theoretical simulations for what it should look like, and it turns out most of the simulations are wrong. So unlike M87, where most of the simulations seem to work well, for Sagittarius Star, it turned out almost every simulation was too variable. Right? So Sagittarius Star, of course, rotates very fast, but it turns out our simulations rotate even faster than that. And so there's some error in our simulations that makes them too active, and we need a way to calm them down a little bit. And so this is an active part of where we're trying to improve our understanding of science. So again, I think Hung-Yi brought this up as the size comparison. And so here we show the exact scale. So Sagittarius Star is about the same size as M87 on the sky, but because M87 is so much further away, it's actually a much larger object. And so here you can see the orbit of Pluto, which is the dwarf planet in our solar system, on top of the disk of M87, compared to the orbit of Mercury, right? And so Sagittarius Star is a much smaller object, but because it's so much closer, it appears larger. And so one of the other important things about the Sagittarius Star estimate was that it let us test gravity again. And so, of course, Hung-Yi talked about how if you assume Einstein is correct and try to estimate the size of the shadow and the diameter of the shadow, that gives you a way to sort of test, if you take an observation of that shadow, you can test if that agrees with what Einstein said the diameter should be. And so this is what we did. And it turns out, both for Saturday Star and M87, agree perfectly with what Einstein predicted. And in fact, it's actually entirely reasonable, and you know, it becomes very hard for non-GR theories to get very similar results. And if you compare this also with tests of gravity done by the gravity wave telescopes, like LIGO and Virgo, you find that, which measure gravity at a very different scale of black hole mass, you find that Einstein's theory of gravity says black holes work the same whether or not they're one solar mass or 10 billion solar masses. So this is really a tremendous range of scales. You know, this is like saying, well, I don't know. I mean, it's so big to think about in terms of regular everyday objects, but it's sort of like saying, my microwave works whether or not it's at 1 watt or 10 million watts, and it'll cook food just as good. And so I think this is really a tremendous test of the theory of gravity. And of course, going towards the future, we have a lot of upgrades planned for the Event Horizon Telescope. Like I talked about earlier, the AJA community has put a radio telescope on Greenland, and that has already participated in EHT observations in 2018, and has participated in 2021 and 2022. And actually, we're processing the 2018 data right now, and we should actually have a publication and some early results probably later this summer. And so we're working really hard on making sure that we can process that. But over the next few years, we're planning on adding a few more telescopes. We're going to add an extra telescope in Arizona, in California, and France. And that'll expand the telescope to make it so that we can make better images and observe objects more frequently instead of just once a year. And after that, there's a plan to sort of evolve in towards a next generation instrument where we'll add a bunch of smaller telescopes at a bunch of different sites around the globe and try to observe 3 months out of the year, or maybe even 6 months out of the year, to get very good temporal or time resolution of the objects we care about. And so like I said, AJA here is extremely involved in a lot of aspects of this. Right now, we support at least half of the current telescopes involved in the array. And going forward, we're going to support, of course, the GLT and help develop a lot of the receiver technology and hardware for a lot of the future telescopes. So here's just a picture of all the folks here at AJA who are participated in this.